Okay, so hopefully you enjoyed the demonstrations with the balloons. And you can see the space right here in your notes page for drawing some diagrams of what happens. So let's start by drawing the blue balloon, for example, and a picture of cartoon Mr. Sadowski. So there's my eyes and my nose, and I'm smiling, and there I am, and my ear, and my hair. And it's a very good likeness, right? Okay, so we started off with the balloons just hanging there, and that meant that if they're just hanging there touching each other, then there's nothing happening. So the balloon starts off neutral, and so I'm going to put some protons in there. Remember, I just got done telling you how there's billions and billions of protons inside any object, but we don't have room for all that. So we're just going to draw 5 protons, and the balloon started off neutral, so we're also going to draw 5 electrons. So that is an overall electrically neutral object. We're going to do the same thing for my head. There's no reason to assume that my head is anything other than neutral, so we'll put 5 protons on my head to indicate take the place of the billions and billions of protons that are in my head. And looks like I'm breaking out some sort of electrostatic acne now. And we'll assume, since my head is neutral, I'll put 5 electrons there to balance them out. 1, 2, 3, 4, 5. And so both these objects start off neutral. And then the balloons were rubbed on either my or Sammy's head. And when doing so, as I mentioned in the video, what we're doing is we're transferring electrons. Because remember, electrons, they're the ones that are far away from the nucleus. They're the ones that can be moved. So electrons are actually going from my head onto the balloon. So maybe I should have warned you. Maybe you didn't want to draw those electrons on my head just yet, because now they're going to move over to the balloon. Now, it looks like I've lost all my electrons. That's not true. I've only lost the electrons I've shown here in the picture. Remember, I still have billions and billions of electrons. I've just lost some of them. So now the question is, how much charge does each of these objects have? That's what the questions at the bottom of the page say, right? And so it says, if I move 5 electrons from my head onto the balloon, what's the charge on the balloon? So take a second, pause the video, and calculate the charge, the Q value of the balloon. Okay, so we're putting some things together. If you just said 5, that's not right. If you said -5, that's still not right either, because, well, you have the right idea. There's 5 electrons that moved. Each electron carries with it a charge, and that charge is given on the chart, -1.6 times 10 to the negative 19th coulombs. So there's 5 of those, and so it's not difficult math here. You're really just going to multiply by 5, and you could do it on your own, but it should be -8 times 10 to the negative 19th coulombs. So that's the charge on the balloon. It gained 5 of those electrons, so here's its overall, it's what we call its net charge. Next question says, if I lost those 5 electrons, what's the charge on my head? Now pause the video and figure that out. Okay, so you can see I've lost those 5 electrons. I'm in excess by 5 of these protons. Now, I didn't gain 5 protons, I'm excess positively, and so the charge on me is +8 times 10 to the negative 19th coulombs. This is pretty much the simplest thing we could be doing here. This is not going to be baffling, right? I think we're okay with this. The next question says, what was the net charge in the system between my head and the balloon before I did anything? And of course, that was 0. Remember, the balloon started off neutral, and my head, we assume, started neutral, so that's 0. And the question says, well, what's the net charge in the system now? Well, you should see that's 0 again. These two values balance back out. And the last question says, well, we have a name for that. That's a name for some quantity that remains the same throughout an interaction. We've seen this before with energy. We've seen it with momentum. And of course, that's conservation. So you don't have room right there on your notes page. You should be going back into your handwritten notes. Let's talk about the law of conservation of charge. Because now we see charge is a conserved quantity. We add it to the list. Mass is conserved. Energy is conserved. Linear momentum is conserved. Charge is also a conserved quantity. And the statement for the charge conservation law is just like all the other conservation laws, that charge is going to be neither created nor destroyed, only transferred from one object to another. So again, this is this new fundamental quality that some objects have, some objects don't. We call it charge. Objects that have charge can interact with other objects that have charge. Now we see charge itself is a fundamentally conserved quantity, that it can't just magically appear in a system, it can't magically disappear from the system. The total charge in the system remains the same as long as it's closed, as long as we account for all the objects within the system. And hey, it's a law, so we're going to box it in as a big idea. Okay, let's go back to our pictures here. Notice we have 3 spaces here, so in our second space here, we're going to draw the 2 balloons. So there's the blue balloon and the red balloon. And I gave extra electrons to the blue balloon, so we know it's negative. You saw Sammy rubbed the balloon on her head, so she gave extra electrons to it. So what's the charge on the red balloon? It's negative also, right? Both of us transferred electrons to the balloons, and both the balloons gained extra electrons. They're both negative. And what do they do to each other? They push each other away with a new type of force. We call this F sub E for electrostatic force. This is what I was saying. Objects with charge, with a net charge in this case 2 negative objects, can exert forces on each other. They interact with each other in a way that they couldn't when they didn't have charge. This is what it means to have charge. They can apply forces to each other. They can interact with each other. And then you saw in the video, Sammy put her head near the balloon and it went towards her, and I put my head near the other balloon, went towards her. So here's a picture of the blue balloon and a picture again of cartoon Mr. Sadowski. And we see that they are oppositely charged, right? The balloon has a negative charge. I lost those electrons, so I'm positively charged, and now there are these attractive forces. The balloon came towards me. In reality, I, of course, was attracted toward the balloon as well, but you didn't see me accelerate because the friction between me and the floor was holding me back. But if I were on a frictionless surface, you'd actually see me accelerate towards the balloon. But, you know, I have so much a larger mass, my acceleration would be a lot smaller, but still, they do attract each other because forces always come in pairs. And so we see we have a new type of force, a force we've never seen before that only exists between objects that have charge, a net charge to them. And it was Mr. Coulomb, after whom we named the unit of charge, who discovered this. So this is going to be Coulomb's law. So now again, we're back in your own handwritten notes. This is Coulomb's law, and here's the equation version of it. F sub E, this new electrostatic force, is lowercase k times this is absolute value of capital Q, absolute value of little q, divided by r squared. And we're going to go ahead and box it in. I'm adding the absolute value bars here. Our book doesn't really have that, so it's not really the way that Coulomb originally wrote it, but we're going to be taking the absolute value of these charged objects so that we don't have to worry about the sign of them. So this equation is going to get us the magnitude of the force between these charged objects. So let's go ahead and define our terms like we always do. F sub E is the electrostatic force, this new type of force that exists between charged objects, but it's a force, so of course it's measured in newtons, there's nothing new, and of course it's a vector, we don't have to write, obviously put the vector arrow there, it's a force. Right? Capital Q and little q, those are 2 point charges, and that's going to be an important distinction about this equation. It only works for what we call these point charges, objects that only occupy a point in space, they're ridiculously small. The units are coulombs, as we discussed before. Now here, already I'm using the word charge in a slightly different way, so it's a little bit strange. We've already introduced this new idea of charge, and it's a little bit confusing, right? Some objects have charge, other objects don't. Objects that have charge can exert forces on each other, they can interact. Objects that don't cannot. But now we also use the word charge to sometimes mean the object that has the charge. We've used the word mass in a very similar way. Mass is this quality that some objects have, really all objects have, right? It's a measure of their inertia, their tendency to resist acceleration. But then we also often refer to the object as a mass, right? We say a 2 kilogram mass. This mass interacts with that mass. And so we're using charge in a very similar way. So now we'll say that an object that has charge is a charge. Okay? It's a charged object. So it's sort of shorthand for a charged object. So these are 2 point charges, 2 tiny, tiny objects that occupy a point in space, and we can only use Coulomb's law if they're point charges. Little r is the center-to-center distance of separation, and of course it's measured in meters, as all distances are. And then we have lowercase k, which is just the number that makes it work. It's a proportionality constant. It is the electrostatic constant. And from experiment, we figured it out into 3 sig figs. We'll use the value of 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. I know the units look a little bit weird, but they're just the units that make the equation work, getting rid of 2 factors of distance, getting rid of 2 factors of charge, and returning newtons for the force, so it's Newton meter squared per Coulomb squared. This unit is up for grabs. It's not renamed after anyone, so if one of you does some Nobel Prize winning work in electrostatics, you might get the units for electrostatic constant after you, and then of course, Nobel Prize, speech, thanks, you know the rest. Now, little k is an important enough number. We're going to box it in, as we often do with these fundamental constants. There are only 6 or 7 numbers that control our entire universe, and this is one of them. This number actually defines our universe, and so if this number were any different, the entire universe would be different. Now, this equation, while very useful, does come with 2 warnings. The first one is one I've already alluded to. It's only for point charges, tiny, tiny objects. However, I will stipulate it also works for spherically symmetric objects. If you have an object that has the shape of a sphere, we can pretend that all of its charge is located at its center, and this equation works just the same, even if it's not a tiny object. As long as it's spherically symmetric, it still works. But that brings us to the second warning. This equation only works if neither object is inside the other, because now we're allowing for the fact that it could be a larger object, but if the other object is inside, then this equation doesn't work, and we have to figure out other ways to do it, but we'll get to those situations later. But this will account for pretty much all situations, most of the situations we'll be doing. The capital Q, lowercase q is not really the larger charge or smaller charge. We just designate them this way, as we did back in gravitation, so we can distinguish between which charge does which role. Alright, so let's go to the problem set. We're just going to try a couple of practice problems here, starting with number 1. So read it, pause the video, try it, and come back. Okay, so if you were trying to use Coulomb's law, you're really off the mark here, because there's nothing with forces here. This is really just a matter of logic. And hopefully you got to this idea that the number of electrons is just this total charge split up by the charge per electron. Right? So if you didn't get that far, we'll go ahead and pause the video now and work it through. Okay, so we're just going to take the total net charge on the object, divide by the charge per electron. You can even literally see the units canceling here. The electrons flip to the top. You put the numbers in, we should get 250 electrons. So it's just saying that each electron carries this amount of charge. If you put 250 together, you get this total amount of charge. So you can see that this is a tiny, tiny number, right? A full coulomb is a tremendous amount of charge. It's very unlikely you'll ever see an object that by itself has a full coulomb or a number of coulombs. Usually we deal with small amounts of charge. Let's look at problem number 3. Read it, try it, come back. Okay, so now we're talking about some more realistic charges here, right? 10 to the -6 or micro coulombs. These are the sort of numbers we'll be dealing with. And I said they're point charges, so we know we can use Coulomb's law. So you just go ahead and put your numbers in. There's nothing fancy here. There's 2 different objects here. I did say one's positive, one's negative, but remember there are absolute value bars here, so you're going to disregard the sign of the charge. Don't even bother putting it in. So this equation will get us the magnitude. Direction will come later. I'm here squaring it because I said they both have the same charge. So certainly you could write it twice if you'd like to, but just a shorthand, save a little bit of room here. I just squared it. And of course, I'm sure you recognize this is in centimeters, so we must convert. And we put the numbers in, we should get 3.60 newtons. And as always, when we do these problems, I hope that you're using your EE or EXP button to use this, to put these numbers in scientific notation in your calculator. Okay, so let's go back to the notes page on the back when we're looking at the fundamentals of charge, the basic facts about charge. Some of this I'm sure you've seen before. We're just going to go through it together. Number 1, there's only 2 types of electrical charge, and of course they're positive and negative. Not to be confused with the objects that carry these charges, like protons and electrons. Those are just some objects that have those charges. There can be other objects that also have positive or negative charges. Positive and negative describe the type of charge. Number 2, I'm sure you know this from back in like 3rd grade or watching Bill Nye the Science Guy. Opposite charges attract, like charges repel. It's exactly what you saw with the balloons. My head and the balloon, which are oppositely charged, attracted each other. The 2 balloons, which are both negative, they repel each other, they push each other away. Number 3, the net or total charge in the closed system is, you might be tempted to say 0 just because that was what happened in that one particular situation, but that's not general enough. That was only for that one situation. More generally is the law that the total charge is conserved. So a system may already have a net charge in it, and as long as no other objects come into or out of the system, the net charge in the system must remain the same, and so objects within the system can exchange charges, but the net charge must remain the same. It's conserved. Number 4, the only subatomic particles that are free to move within atom or between objects are the electrons. And I alluded to this before. Of course, because electrons are far away from the nucleus, they're already in motion. They're the ones that move around. Protons don't. They are stuck inside the nucleus, and then the neutrons don't either, but they don't carry charge anyway, so they're not very useful, at least in regard to what we're doing here. Alright, number 5. This is new. The smallest amount of charge happens to be this number, 1.60 times 10 to the negative 19th coulombs. Well, you should recognize that number. Right? That's the charge on some of the things we've already seen. So this number and multiples of it will come so often, we just say, well, that's a rather unwieldy number. What if we just set that equal to 1? And that's something we do a lot in the scientists to make our life easier. We'd take a more complicated number. We'd say, well, let's just call that 1. We're going to say 1 elementary charge of 1e is this number, 1.60 times 10 to the negative 19th coulombs. So now we can refer to charges in terms of how many e they are. But we go on to say that we can't have half an E or 3.14 E or negative 2.17128 E. In other words, you can't have fractional amounts. The universe won't allow it. You can only have integer amounts of elementary charges. So we say charge is quantized. That's a really good word to know. That it comes in chunks, in lumps of this amount, all these integer multiples of that. As now, if you flip back to the front of the page, you notice that there was a dashed line here because now we're going to rewrite the charge on the proton and electron in this new value of E. And since this is the exact same number, the charge on a proton is positive 1e. Charge on an electron is just negative 1e. And if you've taken chemistry, these are the charges you've been using for protons and electrons. You just left off the e. You just call protons positive 1, electrons negative 1. But in physics, we're a little bit better than that. So we have to have the actual unit there, which is e, telling us that's one elementary charge, either positive 1 or negative 1. But just so you know, we'll pretty much almost always be using the charges in coulombs. Just once in a while, we'll be using this notation. So I want to make sure you understand what that looks like.